This exercise is totally fictional. Do not mix it with reality. There is no proof of the existence of any quantum microscopic rockets. If you have any question, do not hesitate to contact Aitor Vergara and his group.
Schrödinger falls asleep while he's reading Schopenhauer. In the meantime, he dreams with a cat of his paradox. The animal has a microscope through which a strange space can be seen. For the cat's astonishment, the space is full of asteroids and a quantum rocket flies over it. So that Edwin comes up with the next problem. While flying near some asteroids, the rocket, under the influence of a potential V0, gets lost. As long as it goes forward in the x-axis, the spaceship loses fuel. Therefore, its mass decreases in the following way. With the purpose to find it, a rocket containing a radar of range 3x0 is sent from x0 into that space. In that point, the ship's probability function has the following form, where z is greater than 0. What is the lost rocket's energy assuming that the probability of the first search is a half? Position-dependent mass Schrödinger equation has been applied to several physical systems, such as semiconductors, quantum dots, and quantum wheels. In our case, we will apply it to a quantum rocket. According to these mass variation effects, the energy in the dynamic of the quantum mechanical system is described by a Hamiltonian, where special care is taken for the kinetic term. Physicist O. von Ross was the first to suggest the following generalized form of the kinetic energy operator for position-dependent mass model, where m is the position-dependent mass. The constants eta, epsilon, and rho, which are also known as the von Ross ambiguity parameters, can be assumed to be arbitrary, but they obey this constraint equation. For the model analytical solution, let us consider the symmetric ordering form of the kinetic energy operator, as given by this equation. The Hamiltonian of the system is written like this. Now we are ready to solve the problem. Firstly, we are going to lay out the Schrödinger equation, but this time the mass will be dependent of the position. Now we plug the expression of the mass into the equation. Defining the constants A and D, we can solve the differential equation. Now we will apply the condition of the probability that simplifies the wave function. Consequently, the constant C2 has to be equal to 0, and our wave function takes this form. The value of C1 is given by the normalization. We are calculating D, knowing that the probability of being between x equals 0 and 3x0 is a half.
We will now replace the value of d. Isolating the energy, we obtain the following value. Now that we have found him, Schrödinger can return back home and his cat doesn't have to worry anymore.